Okay, so in the past two lectures by Stefania, I think you have learned about the impressive progress in the golden era of experimental neutrino physics and the future prospects. So in this last lecture of this academic training, I will just want to discuss a few of the open questions that drive theoretical research in neutrino physics, some of which I think also open some new experimental perspectives as well. So, as you have seen in the previous lectures, we have learned quite a lot about neutrinos, and we know that the neutrinos that are produced in charge current interactions are not quite those that travel freely in space. They are related by some unitary matrix that can be described in terms of three angles that have values close to those written here. They also have, this matrix also has complex entries, but for the moment we haven't been able to pin those down. And of course this is a very important question because it's the question of whether CP is conserved or not in this sector of the standard model. We also know that the splittings of the states have been very precisely measured, but we don't know which ordering they take. This is, of course, a also very important question from a theoretical point of view, not only theoretical, but also from the point of view of what predictions of the physics behind these neutrino masses the predictions for future experiments, they basically depend a lot on whether you assume one or the other possibility. Now, neutrino oscillation experiments, however, cannot tell anything about what the absolute scale is here, and this is, of course, also a very important question from a theoretical and also experimental point of view. And as it turns out that the best sensitivity we have today to these tiny neutrino masses, to the absolute scale, is coming from looking at the universe we have. Okay? Neutrinos, in fact, have left many traces in the history of the universe, depending on the time at which we looked. These neutrinos could have been contributions, important contributions to radiation or matter if they have a mass. Okay? And let me go very quickly over these very interesting points. So, nucleosynthesis, it turns out that before Lep established this very stringent constraint on the number of neutrinos, the best constraint was coming from Big Bang nucleosynthesis. So the point here is that neutrinos decouple from the plasma at a temperature around 1 megaelectron volt. This happens because this is at the temperature at which the reactions that keep neutrinos in equilibrium with the other particles in the plasma get slower than the expansion rate of the universe and are no longer sufficiently efficient to keep neutrinos in thermal equilibrium. Now, this expansion rate of the universe, this is in a radiation-dominated era, depends very much on the number of relativistic degrees of freedom at that temperature. And of course, each neutrino species being a very light particle, here we are talking about temperatures of 1 MeV, so the neutrinos we have measured, neutrino oscillations, definitely are relativistic at these temperatures, then they contribute to this number of relativistic degrees of freedom. So this temperature depends on the number of neutrinos. Now, what happens at this temperature also is that the ratio of neutrons to protons freezes, because you can no longer have these weak interactions fast enough. And however, at these temperatures, both neutrons and protons are highly non-relativistic, and therefore their thermal distributions are exponentially suppressed with the energy and therefore with their masses. So the ratio of neutrons to protons is essentially fixed by the exponential of the mass difference divided by the temperature at which we are, which is this decoupling temperature. And therefore, the dependence on the number of neutrinos is exponential. Okay? Now, this ratio of neutron to protons is the most important quantity to predict what is the abundance of light nuclei in the universe, which we can measure, and therefore from this measurement we can extract a very good estimate of the number of neutrinos, which, okay, is not, of course, as precise as the Lep number, but for a long time it was the most precise one. So this is one of the major achievements, I would say, of Big Bang cosmology. However, neutrinos can also play a role as dark matter, because if they have a mass, at some point when the universe cools down, at some point they become non-relativistic. Okay? However, since they decouple, I said they got out of equilibrium very early on, they were relativistic, and therefore their thermal distributions were those of a relativistic particle. And after that point, after this decoupling temperature, the number of neutrinos just, the number density of neutrinos just decreases because of the expansion of the universe in a very trivial way. So there are many of these neutrinos around, okay? And therefore, even if they have extremely tiny mass, they can give a very significant contribution to dark matter when they become non-relativistic. So today, for example, and you can see that even neutrinos with masses of electron volt could even overclose the universe. Okay? Now, this would be very nice if the neutrinos by themselves could explain us the dark matter. The problem is that these neutrinos in the time of structure formation, these neutrinos were still very fast moving particles, and therefore this is what we call hot dark matter, and the structure formation would look quite different to the one that we get with less relativistic particles, okay, at the structure formation era. And therefore, they are not good dark matter candidates, but on the other hand, because they give such large contribution to dark matter, we can actually set a bound on their masses, which is very stringent, as you can see here. So, so this is the present situation on cosmology bounds, and here I'm showing on the y-axis, this is the bound that you would get, this is the amplitude that you would get in beta decay, so what you can bound from just looking at the kinematics of beta decay. And here is the sum of neutrino masses, that is the quantity that would be relevant for cosmology. And Planck has set a bound which is about 0.23 electron volt. Other analyses using different data sets have even increased, make it even more stringent. And what you see here, these lines, are from what we know of neutrino oscillations, where we could stay in this, on this plane. Okay? So if the hierarchy is inverted, then we can be anywhere here from oscillation data. If it is normal, we can be anywhere here. Okay? And the present bound from beta decay is outside this plot, but in the near future, Catherine experiment will hopefully set a bound around 0.2 electron volt. Okay? So clearly, cosmology, it seems, future measurements of the CMB and large-scale structure will be able to actually push this limit down significantly. So this is very interesting, of course, a very interesting perspective. So what we have learned about neutrinos, so from a theoretical point of view, they definitely depict a quite different flavor puzzle compared to quarks. As you can see, so they give a different perspective in what we call the flavor puzzle, which is the question of why are these particles spread in this way. Because neutrinos are actually, there is a big gap between neutrinos and the remaining particles of the standard model if we plot them as a function of the mass. Okay? We also have learned that these guys mix in a very different way to how quarks mix. I mean, the CKM matrix is very close to a unit matrix, while the PMNS matrix, the mixing matrix of neutrinos, is very far from it and is rather close to this tri-bimaximal mixing pattern that you can see here. So this is, of course, a big challenge for theorists to explain this difference. And people have worked a lot in trying to understand some of these features, in particular why there are large mixing angles in the lepton sector. And there are essentially two avenues people have been exploring. On one hand, you can say, okay, if you just say that these parameters in the mass matrices are random, then randomness would actually tend to favor large mixings over small mixings. So this is what is called anarchy. Of course, the challenge there is to put then quarks on the same footing, right? Because this would be very different there. People have also explored the order path in trying to understand these large mixings from, as arising from symmetries, either discrete or continuous. And of course, one of the most important leading themes in all this game is to try to put together leptons and quarks, for instance, in some grand unified scenario. Okay? Now, I should say there is, of course, an enormous amount of work in this field. I should say there are many models out there, and I don't think there is any compelling reason to prefer one over the other. Okay? So I wouldn't say there is a smoking gun for any of these possibilities, but this is, of course, ongoing research. However, concerning this difference between leptons and quarks, there is one point which we know, which is that there is a real and very obvious way in which we can find such a difference, and even from looking at the problem at low energies, okay, without having a complete model. And this is, as I explained in the first lecture, is the fact that if neutrinos are Majorana, then we know that there is a new scale that would give rise to this Majorana mass in a gauge invariant way in the standard model, so that if that scale is there, the neutrino mass would be proportional to some unknown order 1 adimensional coupling over this scale. And this scale is the scale, should be interpreted as the scale at which new particles will show up. So in some sense, we are in a similar situation in neutrino physics to where we were with the standard model when Fermi wrote his theory of beta decay. We had an interaction that explained beta decay. We knew this couldn't be the whole story because this interaction would violate unitarity at high energies. And of course, this was resolved in the standard model. Here we have a similar situation. If this interaction is responsible for neutrino masses, then we know this cannot be the whole story at arbitrarily high energies. But however, in this case, we have no clue yet of what the standard model, the new standard model would be. So the big question is if we are in this situation, what originates this operator? What originates this interaction? And of course, there is this very interesting and intriguing fact, which is that if you take this scale to be a Degas scale and the coupling lambda in front of this operator to be of order 1, you get the right neutrino masses. And of course, this would be very interesting from a theoretical point of view if there is a grand unified scale. On the other hand, you have to face the obvious hierarchy problem, because if there is no supersymmetry or any other solution of the hierarchy problem, then generically, a model like this in which you have these extra states, whatever they are, that would induce neutrino masses, they must couple to the Higgs, because we have seen that the interaction involves the Higgs, and then generically they will generate corrections to the Higgs mass that go with the mass of these particles. So if this mass is very large, then naturally the Higgs mass should take finite corrections that are of that order. Okay? This is, of course, just the hierarchy problem. Now, of course, we still hope maybe that LHC will give us some hint of what's the solution of the hierarchy problem, but that clue is still not there. So in this situation, I think it's fair to ask the question, could this scale be lower? Okay? could we really have a scale that is at the electroweak scale, for example? Well, the answer to this question is, of course, yes, if you take a lambda in front of this neutrino mass operator that is small. And then the question comes, what is the natural size for that coupling? And of course, this is a model-dependent question. So you can go and ask, what are the, so in the same sense that the Fermi interaction was solved by the interchange of a W, here we can ask what kind of exchanges could give rise to this mass operator. And you find that essentially there are three possibilities if you consider exchanges only at 3 levels. Okay? There's just 3 possibilities that go under the name of the type 1, 2, and 3 seesaws. And so in the first case, you exchange a singlet fermion in this way. In this case, you exchange a triplet scalar in the T channel. And in this case, you exchange a triplet fermion in this way. Okay? And now you can see, you can read what is the lambda by just reading the couplings in this diagram. You find that both in type 1 and type 3, lambda is of order Yukawa square. Okay? In this type 2 is the Yukawa times some ratio of scales, because this interaction here has dimensions in the case of the triplet scalar. So in any case, what this shows is that generically, at least in all these 3 possibilities that we have, lambda is not really the Yukawa or related to it. It's something that, okay, if the Yukawas is order 1, obviously lambda would be order 1, but if the Yukawa is small, and we know there are small Yukawas in the standard model, then lambda would be squarely smaller, okay? So this is shown here. So if you take, as I said before, the mass at the gut scale, then you can choose for neutrinos Yukawas like the top, and then you get the right neutrino masses. But if you go to much lower scales, at the electroweak scale, you could also reproduce the light neutrino masses with a Yukawa that is of the order of the electron Yukawa. So I would say that before we have a solution to the flavor puzzle, neither of these 2 possibilities look particularly worse than the other. Okay? So the big question is, where is this new scale? Okay? And if we don't have a clue, maybe we should try to see what experiment is telling us, okay? And taking seriously the possibility that the scale might be lower and not at the grand unified scale, whether there are experiments that are already telling us that whether this is possible or not. And so we are looking for generic predictions of these models, and let me show you what generic predictions of these models are. So the most important one, because essentially this observation would essentially demonstrate that such mass operator exists, is neutrinoless double beta decay. And it turns out that this is very generic. There is neutrinoless double beta decay at some level if you have scales responsible for these neutrino masses above 100 MeV or so. Okay? Now, of course, the actual amplitude for neutrinoless double beta decay might be model dependent, and in general it is, but there is a model independent contribution that is always there, and this is essentially, because it's essentially fixed by the lightest neutrino mass, which we have measured. Okay? And this is this famous kind of plot where what you can see here is the amplitude for neutrinoless double beta decay. So this is what you can measure in neutrinoless double beta decay here versus the sum of neutrino masses, again, the quantity that you can pin down from cosmology. And what you see here is that knowing what we know about neutrinos, so this amplitude gets a contribution from the neutrino mass, which is of this form, and we know quite a lot about the mixing angles already and the masses. Okay? So if you plug this, what you know, then you find that if you are in an inverted ordering, you should be somewhere in this contour, while if the ordering of the neutrinos is normal, then you can be anywhere here. Okay? Now, what you see here, this cut here, comes essentially from this plot includes already the present information from neutrinoless double beta decay experiments, I guess they have included the big uncertainty in the matrix elements. So the bound is around here. You can see this is cut precisely. This is at 2 sigma. The dash ones are 3 sigma. This is cut from neutrino-less double beta decay experiments. And of course, it's obvious that there is a race, basically, to try to push the technology down at least 1 order of magnitude in this line, which could, because it would be very nice if one could at least explore the region for one of the hierarchies. Okay. There are other generic predictions of these models. Unfortunately, they are not as model independent as the one I just mentioned. So here we will have to say anything, we will have to consider a model, and that's what I will do in the following. But one of these generic predictions is the generation of a matter-antimatter asymmetry, okay, via leptogenesis. And the other, of course, generic predictions of models like that, if you are at a lower scale, is that these new states could be accessible if they are below what we have explored in energy, highest being the LHC. Okay? Now, again, the fact that these states are there has potential impact in many observables, cosmology, electroweak precision test, LHC rare searches, neutrino-less double beta decay in a non-standard way, and so forth. But again, this is quite model dependent. Okay? So in order to give you some flavor of what we could learn from all these things, from looking at these constraints, I will consider the simplest possibility, okay, which I think is arguably the simplest extension of the standard model that can accommodate neutrino masses and explain why they are so small compared to the other fermions, is the old type 1 seesaw model, which is a very, very simple extension of the standard model. Just add 3 right-handed neutrinos to the model. Since now no gauge symmetry forbids that, I can write a Majorana mass term, and sorry, there should be a C somewhere here, a Majorana mass term for these guys. And as I say, this is how this model would generate the neutrino mass operator that we were talking about. So what is the scale lambda here? The scale lambda here is, of course, the mass of these heavy states. And as I said already, the lambda in front of the mass operator would be proportional to a square of Yukawas. Now, this is a simple extension of the standard model, and in spite of this, it increases the complexity of the flavor sector quite a bit. If you assume that you include only 3 of these states, which is the minimum you need to give 3 light neutrinos a mass, then there are 18 free parameters besides those that we know in the standard model, which correspond essentially to 6 masses for neutrinos, and the description of how these states mix with the leptons, which is described in terms of 6 angles and 6 CP phases, independent CP phases. Okay? So here is basically the kind of a spectrum you have in this model. Of course, this model, if you take the masses to be 0, you just recover Dirac neutrinos. Okay? So what happens is that the 6 states degenerate into they generate Majoranas that are, of course, the same thing as a Dirac fermion. Okay? Now, if you go to very large masses, then 3 of the states get very massive, and 3 get inversely proportionally light. And these are the light neutrinos that we measure in neutrino oscillation experiments. And of course, the hope is that whether we can have evidence for the existence of all this rich spectrum. Okay? Now, the phenomenology of such models, of course, depends beyond neutrino masses, which is what we are after, because we want to learn what lies beyond. Then depends, of course, on what the spectrum of these particles is and the size of the active heavy mixing, which is essentially now when you produce in this model a neutrino state in a flavor state in combination with an electron, muon, and tau, this is no longer a combination of the light states that we have seen in neutrino oscillations, but it also has a component of the heavy states. Okay? Now, this, the quantity that weights what this mixing is the light-heavy mixing part of the full unitary matrix. And this quantity is what essentially fixes how these neutrino states could be produced in charge current interactions, neutral current interactions, or through Higgs production. Okay? Now, these active, light-heavy mixings, of course, this is a complex model, as I said, there are many parameters, but there is a especially interesting way of parameterizing what these quantities can be, and this is the famous Casas-Ibarra parametrization, which essentially is just a parametrization that imposes the constraint on the light neutrino masses. So it uses as parameters the light neutrino masses and mixings that you have measured, and this is of course very useful because then you don't have to tune them every time. You just fix them in the parametrization, and whatever else you can change, you can modify, but not that. Okay? So the way in which, in a completely general way, you can write down these mixings here as the PMNS matrix, the one that we measure in neutrino oscillation experiments, the light neutrino masses that in principle we can, from which we learn neutrino oscillation experiments and cosmology, for example. And then we have the heavy sector, which we don't know anything about, which includes the spectrum, so where the masses are, and then it includes here an R matrix, which is a general orthogonal complex matrix, which contains essentially all the parameters besides the spectrum that we cannot measure at low energies. Okay? Now, looking at this formula, if you ignore U and P here, you find what is called usually seesaw scaling or naive seesaw scaling, which tells you that the mixings, these light-heavy mixings, are essentially proportional to the light to neutrino mass over the heavy. So you can imagine if you plug in electroweak scale there, this is an extremely tiny number. Now, this naive scaling is too naive. I mean, it would be exact if you have just one heavy neutrino, but because you have more than one, these R matrices can have large entries, and then therefore this scaling is quite naive. And in fact, there is much more freedom in these models where this scaling is widely violated. Okay? So within this model, let me discuss these generic predictions. Okay? And the first one was the matter-antimatter asymmetry in the universe. We know that the universe seems to be made of matter, and we have measured very accurately from cosmological observations the number of baryons over photons. And of course, the hope of fundamental physics for a long time has been to answer the question whether such an asymmetry could have arisen from a symmetric initial condition where matter and antimatter were equally present. Okay? And it's also very well known that for that to happen, you need to satisfy the three necessary conditions called Sakharov conditions, because they were first written down by Sakharov. So the first is obviously baryon number violation. If you have a universe which has no baryon asymmetry and you end up with a universe that has baryons, baryon asymmetry, there must be baryon number violation. But we have that in the standard model. We know that B plus L is violated in the standard model by the so-called Sphaleron processes at high temperatures. We need CIP and CP violation, and again, both have been shown to be violated in the standard model. We don't know yet if in the neutrino sector. And you need also deviations from thermal equilibrium, and we know that at least once this happened, this was the electroweak phase transition. Unfortunately, even though all of this is there already in the standard model with massless neutrinos, it doesn't seem to work. And there are essentially two reasons for this. One is that CP violation in the quark sector is far too small. And the second is that the electroweak phase transition is far too weak. Okay? However, with the discovery of neutrino masses, actually we have seen that the lepton flavor sector is much richer than we thought, and therefore there can be new sources of C and CP violation in the model. And in fact, models with massive neutrinos, and this is a quite generic prediction, even though the concrete quantitative prediction of the baryon asymmetry will be very model dependent, leads to the generation of lepton asymmetries in the early universe, and therefore baryon asymmetries, because leptons and baryons are are exchanging asymmetries through the Sphaleron processes. Okay, so now for a long time, the first vanilla, what is called vanilla leptogenesis, was thought to hold only at very high scales. Okay, and I will say a few words in a moment. This is from the out of equilibrium decay of these heavy states that we talked about. Okay, however, it turns out that it might work also at lower scales. So the first to propose this idea was through this mechanism called resonant leptogenesis, where, however, you need to have states that are extremely degenerate in mass, which you might say, okay, this might be not too natural. However, and this is again a similar mechanism, but with a kind of resonant enhancement of the CP asymmetries. However, However, there is another region of masses where actually leptogenesis can happen in a quite natural way, and this is around the electroweak scale. The mechanism here is slightly different to the one before, so let me go well, I will explain it in a minute. So the first thing, of course, is that Sakharov conditions are still satisfied. They were satisfied in the standard model. They are still satisfied here. The CP violation sources, however, will not come from the quarks, will come from the leptons, and we have, as I said, far too many, that as we would like to have less so that the thing would be more predictive, but we have many. We have 3 complex angles in the PMNS matrix generically, and this R matrix is complex and therefore can have also large complex entries. B plus L violation, still the relevance of this is exactly like in the electroweak, in the scenario where you try to get the matter-antimatter asymmetry in the quark sector. So these processes are fast at temperatures above the electroweak phase transition, and below the electroweak phase transition they decouple, they switch off. So at that point, no longer baryon asymmetries can be generated. Leptons might be, but not baryons. Okay? And leptons might be because this model, of course, violates lepton number, because we have Majorana states, and therefore we know that there is no global or gauge symmetry that Majorana fermions would satisfy, so lepton number is violated. And this is quite relevant for the high-scale scenarios. In the low-scale scenarios, however, this lepton asymmetry, so the lepton number violation is not relevant. Okay? It's only the fact that you have independent lepton numbers in the different flavors, which enters in the business, in the scenario. And finally, the big difference between high and low scale is the way in which you achieve this out of equilibrium situation. Okay? So let me say a few words about this. So in the high scale, as I said, the asymmetry is generated in the decay of these heavy states. Okay? So diagrams like these ones generate a difference between the decay probability of a heavy state to a lepton or to an antilepton, and it's this difference that seeds the baryon asymmetry. Okay? Now, it is also a generic and robust feature of this scenario that you need, in order to get the right number for the baryon asymmetry, masses that are very high, above 10 to the 7, depending on the scenario, or 10 to the 9 GeV. Okay? As I said, this is unless an extreme degeneracy between two states exists, in which in case you move to a slightly different version of the scenario where you have a resonant enhancement. The low-scale leptogenesis, however, is quite different. Here we are not looking at the case of these states. Here we are looking at the production, at the original production of these states in the early universe. So these states only couple through the standard model, through the Yukawa coupling, okay? And therefore, these states are produced from the plasma early on with a lepton and a Higgs interacting and producing a neutrino. Now, at low-scale scenarios, the Yukawas will be smaller, okay? And therefore, what happens is that these states scatter very rarely, okay? And because they scatter very rarely, we have the conditions for coherence, okay? So this is why this mechanism is called leptogenesis via neutrino oscillations. Essentially, very much like you can measure CP violation in neutrino oscillations, here CPS phases will induce an asymmetry in the transition from flavor alpha to beta, and the same thing for anti-particles, okay? And this CP asymmetry is what seeds the baryon asymmetry, okay? Now, because if you sum over all flavors, these asymmetries would add up to 0. However, the different flavors are not as efficient, they are not equally efficient in transmitting these asymmetries to the baryons, and therefore a net asymmetry remains for a while, okay? So here is a sketch of what this, the number density of these particles look like in the two scenarios. So in the high scale scenario, because you have large ukavas, these states get into equilibrium very early on, and they are essentially, they have the equilibrium distribution. So this is the abundance over the equilibrium one. So that you essentially are at 1. However, at some point, when you get to a temperatures of the order of the mass of these particles, they decouple, and then they start decaying. And if the decay rate is smaller than the expansion rate of the universe at that moment, then a slight difference between the abundances will arise, and then this is where the lepton asymmetry appears. Now, in the low-scale scenario, you have a smaller ukava, so these guys take much longer to come into equilibrium, to start being produced, okay? So you start with 0 abundance of these guys. As you start to produce them, you see these oscillations here. This is precisely the coherence that you need to generate CP asymmetries, okay? And the blue line here is precisely this baryon asymmetry. So you see it's correlated to this the production time of the neutrinos. Then eventually these guys, or some of them, will get to equilibrium. If all of them get to equilibrium, the whole thing would vanish, okay? But the point is that some of them is quite natural in this scale, in this range of scales, that some of these states might not have reached equilibrium at the electroweak phase transition, and therefore a net baryon asymmetry will survive, okay? So if we would have plotted this longer, then the whole baryon asymmetry would go to 0 at some point exponentially, but the electroweak phase transition happens before, and therefore what happens with lepton asymmetries after that is completely irrelevant for baryons, okay? So here the condition for this to happen is that some of the states, the scattering rates for some of the heavy states is smaller than the expansion rate of the universe by the electroweak phase transition, which if you put numbers is quite natural for this range of masses, okay? So, of course, the big question about the matter-antimatter asymmetry is whether it's testable, can we predict this number? And of course, the important message is that the baryon asymmetry cannot, even in a specific model, cannot be determined from neutrino masses and mixings only, okay? This is very clear because, you have many more parameters in the model, and they contribute in a significant way to the baryon asymmetry. So you need more information from this heavy sector, okay? Obviously, if you have a high-scale scenario with states that are at the 10 to the 7 or 10 to the 9 GeV, it will be extremely difficult, if not impossible, to actually test this, find these states and measure other observables. However, this is possible in low-scale scenarios because these ends are lighter and therefore can be produced in the lab and could, in principle, be detectable. And here is just one example, okay? I just give you one example. Here, what you see on this plot, so we are plotting here the mixing of one of these heavy, so this is the low-scale scenario, so the masses of these guys at around, as you can see here, around the GeV. And what we are looking after here is what is the mixing of these states, for example, with the electron flavor, okay? Because these are quantities that, in principle, if we have an experiment that produces these states, could measure this mixing, okay? Now, what you see here are these color regions are posterior probabilities, assuming I have explained within this model the baryon asymmetry. That's it, okay? I let all the parameters vary as they like, and I just evaluate posterior probabilities on this plane, okay? Now there are two colors here. Of course, if you do a Bayesian study, you depend on priors to some extent. And it happens also in this low scale scenario that asymmetries tend to be enhanced if you have degenerate states. I mean, this is quite generic, both in high and low scales. The problem is that in this case, you don't need such high degeneracies. So the blue line here is a study in which you let the masses vary independently, okay? And therefore, of course, you are penalizing the degenerate solutions because your Bayesian analysis doesn't want to go into a measure zero volume, okay? So this is what you would get if you penalize the degenerate solutions, the blue line. If you don't penalize the degenerate solution because you think that it could be natural for parameters to be there, you would be doing a different study in which you let this degeneracy be anywhere, okay? And if that's the case, then you enlarge the parameter space. So what I want to show you in this plot, however, is the comparison of these regions with, first of all, this shaded area here is what the present constraint existing in searches for these for such states in different experiments, and the empty regions correspond to future prospects of different experiments. Okay, so these two here are essentially for the lower masses below the meson masses. The best way to search for these states is through rare decays of mesons, and the different vertical lines that you saw here correspond essentially to meson thresholds. While at higher masses, the best way for searching for these states is through set decays, okay, that produced a very a golden signal, which is a displaced vertex, okay? And this is, of course, a search that was carried out already in LEP, okay? So now we have clearly a significant region of parameter space that we could test, okay? So now I want to sit down here in this point here, which is within the sensitivity of SHIP, and I want to ask myself, if I have states that lie there and they explain the Baryon asymmetry, can I measure them, and from that measurement predict the Baryon asymmetry? That's the next question. And what can I measure? Well, if the states are there in the SHIP range, then I could, in principle, measure. There are two states, by the way, that enter in this mechanism. Okay, we are in the simplest model with just two neutrinos. So in principle, I could measure both masses, and I could measure their mixings to electrons and muons. Okay, and of course, I could measure the mixings to taus, but this will be harder, so I will just stick to this. And then, as you have heard in previous lectures, future experiments will be able to pin down the delta phase in the PMNS matrix. So let me assume I just have these observations. Then what can I say about the Baryon asymmetry? So this is what this is again a posterior probability, but now of these measurements. So I assume I have measured these quantities with some precision, and then I do a posterior probability on the plane, the Baryon asymmetry versus neutrino-less double beta decay. And I'm not assuming anything else. I'm letting all the parameters in the model vary as they want. Okay? So there are two regions here, the pink region, or the orange, or whatever color this is the one in which I only include SHIP measurements, but I don't include the measurements for delta, for the CP phase, from future oscillation experiments. And in the blue, I include also delta from future experiments. And what you see here is the range I expect for the amplitude of neutrino-less double beta decay if I would just have the standard contribution to neutrino-less double beta decay. So you see there are differences in the amplitude of neutrino-less double beta decay in this model compared to what I said at the beginning, which is this model-independent minimum contribution to neutrino-less double beta decay. And this is a very important observation. Essentially, this quantity plays a big role if you would not have any information on n beta beta. it would be very difficult to say anything about the baryon asymmetry. It's a strong correlation there you have to resolve, okay? So why is this? So this is because these heavy states also contribute to neutrino-less double beta decay. In general, the amplitude for neutrino-less double beta decay has the standard contribution from the light states and a contribution from the heavy states. Now, this contribution from the heavy states implies that in this diagram, there is a heavy state being exchanged, and the nuclear matrix element will be very highly suppressed if the mass of this guy is above the typical momentum transfer in this process, which is 100 MeV or so. So this term, if the mass is very heavy compared to this 100 MeV, it will be negligible, and this is where we get the standard contribution. But it turns out that for masses in the range of the GeV, this contribution is not so small, and in fact, it is this contribution to neutrino-less double beta decay that brings essential information about some of the CP phases, in fact, and other unknown parameters, which allow us to resolve these degeneracies. Okay? So imagine that tomorrow, neutrino-less double beta decay will measure something with some very aggressive error bar. You might be able to even pin down the baryon asymmetry here up to a sign. So this is, I think, one of the, well, I think the only example I know where without any additional theoretical assumption, you can actually hope to predict this quantity. So this is a kind of GeV miracle, because it's at the GeV range where all these measurements, the synergies of all these measurements get maximized, okay? So let me go beyond this baryon asymmetry. I said that generically also these models predict there are other states, so we can ask ourselves where these states can be beyond the explanation of the baryon asymmetry. And of course, an obvious question is, can they be even at lower values, at least some of them, okay? Now, it turns out that sterile neutrinos below 100 MeV or so, again, can strongly modify all these cosmological observables, either because they contribute as dark matter or extra radiation, depending on the time in the evolution of the universe. And typically, so what happens is that if you take this simplest model I have been discussing, and you impose that this model explains the light neutrino masses, you can actually show that if the lightest neutrino mass that we haven't measured yet, we don't know the scale, is above 3 × 10⁻³ electron volt or so, then only cosmological measurements would tell you that it is impossible that these states are below 100 MeV, okay? So they must be higher than that. So we are excluding a very large region of parameter space. If the lightest neutrino mass is below 3 × 10⁻³ electron volt, then two of them must still be heavier, but one of them might be anywhere, okay? And this is the famous new MSM. So this is the model with this situation, with these masses, this mass spectrum, is also called new MSM, where one of the states, this state that is free to be anywhere depending on what the lightest neutrino mass is, could be at the keV scale, and then it could be a warm dark matter candidate. Okay? It's not hot because it's heavier than the electron-volt neutrinos I was referring to before, and it's still a viable candidate for dark matter. And of course, there was a very exciting news a couple of years ago when an unidentified line, the 3.55 keV line, X-ray line, was observed in clusters, in various clusters. Now, how you get that X-ray signal from such a particle, when this particle, although it's very, very long-lived, of course, it can decay rarely through a light neutrino and a photon, and because it's a two-body decay, the the photon energy is just fixed by the mass over 2 of the original particle. So this means that a 3.55 keV line would imply a state of 7 keV. Now, I don't want to say more because I have to rush. So the other question is, where are the new states? And the plot has disappeared. Great. God. Okay. So there was a plot here, which is essentially again, mixing versus mass, okay, of these states. And I was plotting before some, so this is essentially the plot that I draw. Oops. Up. So a plot like this, okay, here I was stopping at 10 to the minus 6, so this is a relatively small mixing, okay. And now what I wanted to show, but I cannot, is the plot, how it looks if I increase that mixing to 1, okay. Because what happens is that if I take out this and I will show you the plot, then you'll see that there are many other constraints coming from colliders, electroweak precision tests, searches for lepton flavor violating processes like mu to a gamma, etc. And in particular, in the highest mass range, of course, the only constraint really comes from LHC, okay? So here is one of a typical LHC searches. Of course, searches for these particles at LHC had been carried out by both collaborations, and this is a typical signal for that, with three lepton signal. Now, what you see here is what the kind of constraints they can set on the mixing, heavy muon mixing in this case versus the mass. And this is above, so these constraints in this mass range are the best, but nevertheless, they are rather poor in the sense that the mixings that you can bound are about 10 to the minus 2. Okay? And remember this seesaw scaling, which was telling us that this mixing should scale like the lightest neutrino mass over the heavy mass. So this is many, many orders of magnitude above what you would naively expect. Okay? Now, in a not so large mass scale, I think it's still possible that LHC could do an extra effort in improving LEP constraints there by searching for these displaced vertices, both through W decay like here or Higgs processes. And there is some, I think, okay, this hasn't been carried out by the experimental collaborations yet as far as I understand, but it could be that LEP constraints could be improved slightly with LHC. Now, as I was saying, if you take this naive seesaw scaling, that the mixing square goes like the lightest neutrino mass over the heavy, the bounds that you can set from colliders will be extremely poor. Okay? However, this is naive, and in fact, in some cases, you would say that, so it can, in the seesaw model, it can happen that those mixings are much larger. We have these complex metrics that can have large entries, so it can be orders of magnitude higher than this. Now, in some cases, that choice is unnatural, okay, and then we don't like it, okay. It involves some very fine-tuned cancellations that we don't like. However, it could also be technically what we theorists call technically natural, because it's based on asymmetry or approximate global symmetry, like a U1 lepton number. So imagine I take again this very simple model, but now I impose that the mixings that I am allowing are such that they satisfy that if I assign lepton number 1 to one neutrino and lepton number minus 1 to the second, that this is the Lagrangian is symmetric. Okay? So if I do that, then I can only write the mass term changing 1 to 2, and I can only write a Yukawa coupling for one of the states. Okay? Now, this theory, then, the standard model plus this, would satisfy exactly a U1 lepton number symmetry. And therefore, it will not induce, no matter what this coupling and this mass is, it will not induce neutrino masses. Okay? So in particular, this Yukawa coupling will be unbounded by neutrino masses. It would not be correlated to neutrino masses. Of course, you need neutrino masses, but then what you do is you accept only terms that break this symmetry by a small amount, and therefore it is stable under radiative corrections because it's based on asymmetry. And this is, okay, there are many models of this type, and the most famous go under names such as the inverse seesaw or direct seesaw. The differences are what small breaking terms we switch on, okay? So the most generic case would be to switch on all of them at the same time, okay? But it's important, I mean, the important message is that this is a subclass of the type 1 seesaw model. So in the parametrization I wrote down, this would be just some part of this parameter space would correspond to this situation. Okay? Of course, it might be very difficult to look for such symmetric regions if you do just a complete Bayesian study where you let all the parameters vary as they like. But these scenarios are interesting, of course, because they can be, I mean, what you gain basically is that even if you are at the electroweak scale, where the naive seesaw scaling would tell you the mixins are very small, you can have large Yukawas there, okay? And therefore, there are many, I mean, there is a very rich phenomenology for this type of models. In particular, there could be contributions to mu to E gamma, and future experiments can explore further this range. And of course, LHC, as I was mentioning, because then the mixins could be larger. Of course, there are also many less minimal models. I was talking about the most simple one, but there are models where these extra states have gauge interactions, and this, of course, improves the sensitivity of future experiments because they can be produced much more easily through the gauge interactions, and this is the case for the type 2 and type 3 seesaw models. And LHC, well, I will show you, yeah, and here is, for example, one of the searches at LHC with this beautiful signal, which is the production of two double-charged triplets that would decay to two same sign leptons. Okay. Now, constraints from LHC, you can read from here. Basically, already are bounding these masses to be above half TeV or so. So I will just conclude because my time is over. The results of many beautiful experiments have demonstrated that neutrinos are, for the time being at least, the less standard of the standard model particles. There are many fundamental questions that remain to be answered, however, whether neutrinos are Majorana particles, which imply immediately that there is a scale of new physics, whether there is CP violation in the lepton sector, and whether this could source the matter-antimatter asymmetry. How do we understand lepton and quark flavor in a unified way? A new physics scale that could underlie this Majorana nature of neutrinos could explain the smallness of neutrino masses with respect to the remaining fermions, and maybe solve other mysteries that are there, like the matter-antimatter asymmetry or dark matter, etc. There is a clear complementarity of different experimental approaches, as I showed you in a concrete example: neutrinoless double beta decay, CP violation from neutrino oscillations, direct searches in meson decays, and also collider searches, particularly of displaced vertices, are particularly interesting. And this holds in well-motivated models with low scales, and I think these are searches that should be done. Okay, so I think I'm done with the lectures and the academic training course. Thank you. Questions? Yeah.
You had this plot with m beta beta for the neutrinoless double beta decay. What is that exactly, m beta beta?
M beta beta?
Yes.
Okay, so this I showed.
I mean, is it not? My question is just: is this not given by the nuclei?
By the what? By
the nuclei, by the
no
mass of the nuclei.
No. So the when you set a bound on the lifetime of this process, this lifetime will depend on three things. There is a phase factor that is computable. There is a nuclear matrix element that you don't know very well. Okay, you have estimates, but they are very uncertain. And then there is a contribution from the neutrino mass, which is this m beta beta. So if you look at the neutrinoless double beta decay diagram here, you see there is a neutrino being exchanged here, and it must chirality flip. So there is essentially a mass insertion. And because this is an electron here, you would get the mixing angle of, I mean, the element of the mixing matrix electron to whatever neutrino is massive neutrino is propagating, and then you have to sum over all the three. So this is the contribution from the light neutrinos to this diagram. Okay? So the whole process will depend also on nuclear matrix elements. But what I call M beta beta is just the part that contains the information on neutrino physics. Okay? Is that answering your question?
Not quite, because when I'm looking for a double beta decay, neutrino double beta decay, I know the original nucleus and the final nucleus, and
beta decay. You are talking about double beta decay?
Yeah, neutrino is double beta decay.
Yeah. Mm-hmm.
Beta decay. So I know the masses before and after, and I can just what I'm looking for if I see it or not. But I mean the mass of the betas is the energy of the betas will basically be given by the mass difference, right?
Yeah.
So if what freedom do I have, or is it just from seeing that from seeing the decay in a given nucleus or not? I mean, there are not too many nuclei where I could see the decay.
So I explained a bit.
I'm not quite sure what the diagram means. How I should try to fill that plot, because every decay would only give me 1 point, probably, right?
Yeah. No, so I don't know if you're asking this question. I mean, so of course, there are many isotopes that have been where this process has been searched for, okay? And there are different limits for the different isotopes. The best ones come from both germanium and xenon 136 at the moment, okay? So what people look is, is the energy of the sum of the electrons, the two electron energies should be fixed, right? Because there are no neutrinos in the final state. And you search there and you don't find a peak, and then you set a bound on the lifetime of this process. Now that lifetime depends on matrix elements, which depend on the isotope, and depends on some quantity, which is just coming from neutrino properties. And then assuming you know the matrix elements, and there's estimates from nuclear physicists of these matrix elements for these different isotopes, you extract a bound on this quantity, which is what we are interested in here. I didn't talk about the nuclear part. But, okay, we can discuss.
Different nuclei, I could learn different things. I mean, if I see it, I think there's about a dozen or so nuclei where double beta decay is possible.
Yes.
So from some I would learn
more
about the mass hierarchy than from others, because some would be extending more to the lower.
Well, you have more sensitivity. I mean, you have reached, well, if the matrix elements are smaller for a given isotope, then it will be suppressed, okay? So it will be harder to get a signal. I mean, at the moment you are, of course, right? And then so each isotope will give a different bound, okay, on this quantity, yes. So are you asking about the actual bound for the different isotopes? I had in the first lecture, I had a table with.
No, it's rather potentially what one could extract from which decay.
No, I mean from each decay, from each isotope. I mean the different isotopes will give a different matrix element, but they will all be proportional to this, and this is what we are interested in fundamental physics. This quantity, okay? So they will give less or more sensitivity to this quantity. That's it, okay? Of course, maybe here the dependence on, if you have extra non-standard contribution coming from heavier states, maybe these, these matrix elements on the dependence on the mass that appears here might also depend on the isotope. Yeah, right, Jacobo, or a little bit. Not much, but maybe there is some farther. But I mean, here we are looking for what this process, the fundamental physics information that this process can give, and then it's the same for all isotopes. It's just this combination. Yeah.
Can you see a little bit more about the minimal model? What else does it have? It has exist or what?
No, it's just that all type 1 seesaw model, except that, you mean the one that gives this, for example?
Yeah, that one.
So this is just the type 1 seesaw model with 2 neutrinos, because that's the minimum you need to get the splittings that we have observed, okay? So 2 neutrinos, so the minimum number, and just generic mass matrix here, and generic Yukawas. That's it. Yeah.
So Stefania was mentioning yesterday the search for sterile neutrino at the short baseline.
Yeah.
How could such a neutrino enter in this scheme, or it is?
Yeah, that's a good question. So let me go to this cosmology thing. Yeah. So yes, one possible. I mean, usually these sterile neutrino signals are interpreted in a very generic way, in which you just have an extra state which doesn't couple to the set, and then it mixes with all the neutrinos. Now, this is a phenomenological description, but definitely this model doesn't make any sense because it violates gauge invariance, okay? Now, if you try to make a model with light neutrinos, like electron volt neutrinos, and maintaining gauge invariance, this could be also a possibility here. You could have one of the states to be at the electrovolt scale, and in fact, you could fit, with such model, you could fit the anomalies, the anomalies. Now, yes, Stefania said there are experiments that will search for that. I don't know if she mentioned also that cosmology actually is setting very strong bounds on that possibility. So if you would trust cosmology alone, you would say that possibility is excluded by cosmology. That's one point. And of course, there is also strong evidence from IceCube recently that I mean, muon disappearance. I mean, all these models, the problem is that all the reactor anomalies that we have seen involve electrons and muons, right? Because the LSND involves neutrino, electron to neutrino, muon, or the other way around, and reactors involve neutrino electrons. But if you want to explain the LSND anomaly, you need that whatever state this is should mix also with muons. And then you should see disappearance of muons, and this hasn't been seen. So there is, I mean, still the reactor anomalies remain a question, but this explanation of the reactor anomalies is not a very good fit of the data, okay? And definitely if you would trust cosmology, that would be excluded by cosmology to a high significance already. Yeah.
Is it correct that the cosmological limits on neutrinos are all calculated on the understanding that neutrinos behave with a standard weak interaction, but sterile neutrinos do not? Yeah? But sterile neutrinos are, I assume, pair-produced in the right amount at the initial Big Bang. So they exist from the very beginning, and as you say, they modify quite strongly the evolution of the universe. So why doesn't, okay, what is the bound which is coming on the existence of, say, a sterile neutrino, a fourth sterile neutrino of 1 electron volt mass from the cosmology? You seem to say it is almost excluded. Yes? True.
Yeah.
So why do people continue discussing sterile neutrinos?
Well, I guess, as usual, there are always caveats in everything you do in life, almost.
What is the caveat? What is the caveat?
So the caveat in the cosmological analysis, I mean, there are people that have worked out possible ways around those bounds, like, for example, assuming there is something else. These neutrinos might have secret interactions, and then the cosmological bound, you can make it disappear, okay? Of course, this is all cooked to avoid the bound, okay? There is no particular, I mean, these models are not particularly interesting in any other way, but this is a possibility, okay? The other possibilities, of course, these cosmological analyses are very complex, and they depend on priors, and you know, so the systematics of this, of course, if you talk to a cosmologist, they would say it's absolutely robust, but yeah. But there are ways around with extra physics. you can have an electron volt neutrino, an extra physics that would essentially amount just to exclude cosmological bounds and have no other impact, unfortunately. Yeah. Yeah. Yes.
I want to comment that momentum transfer doesn't depend on nuclei, isotope of nuclei, because of this transfer value comes for actually the pion mass. So if you go to one nuclei to another isotope, it doesn't change, very weakly change. So this M beta beta is almost independent. I should say more strongly, it's independent on nuclei somehow with isotopes you form. Okay, Pilar, I want to ask you something. Am I understood correctly that departure of unitarity of 3 by 3 is PMNS matrix? It could be large, even right-handed neutrinos are heavy. So in other words, is a ratio M, because this departure of unitarity must be proportional to MD over MR, something like this. So if MD of R will be small, you will still have large departure from unitarity of 3 by 3.
No, I mean, the larger M is, the smaller that contribution would be, right?
Yeah,
I mean, if you trust the scaling. Of course, if you increase the mixins, at some point you start seeing it non-unitarity violations, and this is one of the relevant constraints. However, this constraint comes at much larger. I mean, unfortunately, this is the plot that didn't show up. Yes, there are constraints from non-unitarity and electroweak precision tests, but this bound the mixins much higher than in the plots that you could see here.
In your case, it seems to me that you have that. So you have.
I mean, if you have these states, you have that. Of course, you have that. Okay. In this model, definitely you have a breaking of unitarity of the PMNS matrix, but the effect is extremely tiny. Okay. Yes.
Sorry, on semantics. It's a PMNS matrix. Now, MNS, this stands for the 3 Japanese who were discussing flavor oscillations, which is a quantum mechanical origin, which is quite standard and possible. To my understanding, Pontecorvo has discussed something completely different, which leads to the same formula, but he discussed neutrino and antineutrino oscillations, which require, by necessity, an unknown interaction which does not exist. So your apples and pears have been thrown into the same basket for no good reason. Why?
Well, I'm not a historian here, so I maybe some of you could comment on this. I think Pontecorvo has, I mean, if you think of, maybe he described the oscillation better than, I mean, I think he's, I don't know, I mean, to me, I know that his first paper was on neutrino antineutrino oscillations, I know, but I think he, maybe you can comment, yeah.
Paper with Gribov is neutrino, electronic muonic neutrino oscillations. Paper with Gribov.
Yeah, that's right. Yeah. Later on, it was not the first paper.
This was after MNS. So, my point is
Okay, so thanks, and we stop here.